This will be the discussion section for Laboratory 27, renal function. So we'll look at the discussion of it. We talked a little bit about some of those things in the introduction for the lab. It's a quick summary of some of the vascular anatomy of the kidney. Understanding how the kidney works, I think, is essential to understanding how some of this information works in terms of the kidney. So looking at the vasculature of the kidney, the kidney is an example of a portal system where we have two capillary beds in series. The first capillary bed is called the glomerulus or the glomerular capillaries. So that's right here, the glomerulus. And the other set of capillaries is right here. Up here, those are the peritubular capillaries. So the other important vessels, here is the afferent arterial. So A means to carry towards, so that brings blood into the glomerulus, and then exiting the glomerulus is the efferent arterial. So A comes first. Afferent means to carry towards, efferent means to carry away, but A comes before E, so you know that one's first. Another important part of this is something called Bowman's capsule. Sometimes it's just called the capsule nowadays. And what happens is this actually has two layers. One layer that sits on top of the glomerulus that helps it filter and actually makes it a more selective filter. And the other one is just the outside area, sort of like a cup that directs fluid into this area. So this purple F right here, if you look over here on the key on the right side, says filtration. And filtration means we're taking things out of the blood and getting it into the tubule. Okay, so as we follow the path of the tubule, then you have this first part that's kind of shown here, a little bit wavy. So that's called the proximal convoluted tubule. This part right here, stay with this, is called the loop Henle. So it goes down and then comes back up. And then this part is the distal convoluted tubule, and this area right here is called the collecting duct. If you'll notice, the peritubular capillaries, for the most part, run alongside of this. And what happens, and this is a way simplified version, but what happens is we can take things out of the tubules and back into the body. That's that green R there, that stands for reabsorption. Or we can take things out of the peritubular capillaries and stick them into the tubules themselves, and that's called secretion. If you look at the end of the tubule down here, where you see the E and the yellow arrow, that means excretion. That's what's going to become urine. So basically, if something gets filtered into the tubule and it stays here, it gets excreted out. So we spit out this urine. If it gets into the tubule and we take it back into the body through reabsorption, then it's not going to be in the urine. Or if it doesn't get in the tubule and we want to get rid of it, we can actively secrete it into the tubule to pee it out, basically. So I don't like this diagram for a couple reasons, but one of them is it makes it appear that reabsorption and secretion occur the length of this. And to be honest, most of the reabsorption occurs here early and most of the secretion occurs here late. In the what's called the distal convoluted tubule. And there's very little, as an example, of reabsorption secretion that happened in the collecting duct. And so it's really, a little bit simplified here, but that's kind of the way the kidney basically works. And again, in lecture, we'll talk much more about that. So this also identifies the tubular elements, right? So, we've got vascular elements, which is the afferent arterial, the glomerulus, which is our filter, the efferent arterial, and then the peritubular capillaries going all the way through. And then my tubular components, which we mentioned, would be Bowman's capsule here. This first one is the proximal convoluted tubule, and then the loop Henle, and then the distal convoluted tubule, and then eventually the collecting duct. So What we're sort of looking at is we're looking at something called the nephron. Actually, not technically all the parts I mentioned are part of the nephron. And again, we'll worry about the details in lecture. So one of the major functions of the kidney, and the kidney's got literally over 50 different functions, although in class we'll narrow it down to probably 6 or so. But the kidney has a number of different functions that allows it to do certain things. And one of its major functions is filtration. So the job of the kidney is to filter blood. And basically what it does is it filters blood into the kidney. The things that we don't want, it leaves in the tubules and we pee it out. When fluid leaves the glomerulus, right? Since the glomerulus is a capillary, the fluid in there would be the liquid portion of blood, which was called plasma. And if it gets filtered across that wall of the capillary into the lumen of Bowman's capsule, right, into that space of Bowman's capsule, now it becomes ultra filtrate, right? It's called ultra. Again, we'll talk about a lot in lecture, but it would be important for us to understand in the lab as well. It's called ultra because it's protein and cell free. So the protein doesn't usually get filtered across the wall of the capillary, neither do the red blood cells, white blood cells, or platelets. So the large molecules don't get filtered through. The smaller ones do. And that's important in terms of how the body works. And just, as an aside, the reason why that happens is if we were to filter, let's say, red blood cells into the tubules, well, the result would be either the red blood cells would get peed out, or we'd have to somehow reabsorb them back into the body. And so by not allowing them to get there in the first place, it makes it easier not to have to worry about them if they do get there. Humans already have a hard enough time maintaining enough blood volume and blood cells, right? I mean, from the cardiovascular section, we talked about, 20% of women are anemic and even 3% of men are anemic. So, just if we peed out a whole bunch of blood all the time, it would even be, virtually impossible to keep enough blood for us to function normally. So, when the kidney makes filtrate, then, like I said, some of that gets reabsorbed, and that comes out of the tubules and back into the blood. So those are the green arrows. Notice their direction out of the tubule into the blood. And secretion, that's the S's, that's from the blood and into the tubules. So normally speaking, the things we want to hold on to, the things we want to keep, we reabsorb, and the things we don't want to keep, we secrete. So it's pretty simple. Now, when we look at how this works in general, right? Here's my plasma entering the afferent arteriole. We're going to say 100% of that fluid is plasma, and that's the 100% we're starting with. Well, typically, somewhere to between 10 and 20% of this fluid becomes ultrafiltrate. It gets filtered, and the other 80% stays in the glomerulus, right? So it's still plasma. And then it goes through the peritubular capillaries and eventually return back to the circulation. So the 20% that gets filtered, right, we reabsorb most of it. Okay, so it says over 19%. What it's talking about is of this 20% of this whole 100%, right? 19% of that, greater than 90%, is returned. Or another way to say it is, of this that gets filtered, 98, 99% of the fluid that gets filtered gets returned back to the body. So that's called the urine production rate, the amount of urine that you produce in a given amount of time, and typically measured in mils per minute. So in order to measure urine production rate, we need a volume. Okay, and again, from our sample data, it was 36 mils. We need a time, that's that void interval time. Somebody emptied their bladder, started a timer, and then stopped it again when they went pee. So 30 minutes had passed. So we can take 36 mils, divide by 30 minutes, and get our urine production rate of 1.2 mils per minute. Now, a normal range for people is about 0.5 mils per minute to about 5 mLs per minute if you're drinking a lot of water or something. Once you start to get close to 5 or above, it starts to be excessively large and does indicate sometimes a pathology. The most common one would be diabetes, as an example. So what happens in the kidney then is it's the combination of filtration, reabsorption, and secretion that determines the concentration of your various ions in plasma and urine. So if you have excessive sodium, right, really the only way to get rid of it is to pee it out. And so that's going to be controlled by other factors. We'll talk about some of those in lecture. But the bottom line is, the urine is a very useful tool then to get rid of stuff that we don't want to keep in the body. As an example, we've talked about this a couple times this semester, but one of the ways we measure, one of the ways we maintain pH balance in our body is by, the urinary and respiratory system. So if we breathe out more CO2, since CO2 acts as an acid, it's one way to get rid of acid. Or we could actively secrete hydrogen ion into our urine to get rid of the acid that way. In addition, we can go the opposite way and retain CO2 or retain hydrogen ion to help, change pH back depending on what the condition was. And pH is a homeostatically regulated variable, so we have mechanisms to both increase it and decrease it through negative feedback and antagonistic control. So a couple reminders with pH. pH is determined by your concentration of hydrogen ion, right? So remember H plus in brackets is concentration of. Urine pH is typically lower than the blood. Remember, blood pH is 7.35 to 7.45 with an average right around 7.4, right? And that could drop because of excessive CO2 or lactic acid, like if you just exercised or something. But typically it doesn't change appreciably during those things because of buffers and other ways we control that. Like if we make more CO2, we breathe out more CO2, typically. But the urine pH typically tends to be lower because it's more concentrated. And that's, again, because we reabsorb most of the fluid back, but we don't typically reabsorb the same amount of hydrogen ion. So the hydrogen ion becomes effectively more concentrated. And if the hydrogen ion becomes more concentrated, then the pH is going to drop, right? So pH is going to go down. So that was that. The specific gravity is a measure of the concentration of your urine. The higher the concentration, the higher the specific gravity you have. Now, this chart doesn't work great because it's on the computer and things, but here's a chart that basically shows the urine color test. The lighter the urine, the lower the specific gravity. And kind of think of it this way. The lighter the urine, the more it's like water, so the less stuff it's going to have in it. Urine, right, is water with a whole bunch of stuff in it. So we expect the specific gravity to be slightly greater than 1. And again, the typical range, 1.003, 1.005-ish, up to about 1.040. So if your specific gravity was like 1.003, that would be up here in this really light urine color test next to the one that you just barely see because it's so light, while the 1.040 is going to be somewhere down here in the 7 or 8 range. And again, there could be other things that cause that color change. And there are certainly some dyes that you can ingest that are going to do that as well. But the bottom line is, in most people, it tends to be a decent test in understanding what's going on. For the clinical examination of urine in 9.3, we'll look at those things in a second. But let's go back. So note, in 9.1, right, we looked at urine pH, right? Earlier, we looked at the urine production rate, right? So in 9.1, urine production rate, urine pH, urine specific gravity. Notice we skipped to 9.3. So because of the complication with chloride concentration, and because we're not going to get into that detail at all, even close to it in lab, and not really that close to it, to be honest, in lecture either, we're just going to skip the chloride concentration aspect for exam purposes. So don't worry about chloride concentration and how to calculate it for exams. All right. So getting to the clinical examination with those dipsticks that we talked about before, sometimes called clinisticks, or got a bunch of other names too, chem strips that you might see. Again, we're worried about these 5 things, right? And so these 5 things we looked at for our urine would be glucose, protein, bilirubin, and ketones. Okay? So those are what we're looking at for those things. So again, all of these tend to be very little in urine. Okay? So we don't expect to have much or any at all, if possible. If you have excessive glucose in your urine, which would be more than 0, it's called glycosuria. If you have protein, it's called proteinuria. If you've got bilirubin, it's called bilirubinuria. If you've got ketones, it's called ketonuria. If you got blood, it's called hematuria. Even though it looks like a T, it's pronounced CH, hematuria. Or you could call it hemoglobinuria if you had hemoglobin specifically. But oftentimes hemoglobin and blood are used interchangeably. It's almost impossible to have one without the other. So you should know those scientific names. One of the things that's just kind of interesting is looking at why these different things should be very low or 0 in the urine, right? So we don't expect any in the urine of glucose, as an example. And glucose, if you think about it from an evolutionary perspective, is we spend a lot of time and effort getting that glucose, getting that energy. And if we just peed it out, then that wouldn't be very effective for maintaining enough energy to function. And so what happens is, because glucose is relatively small compared to proteins and blood, the cellular elements of blood, it gets filtered through the apparatus within the kidney. And so there's really no way to prevent the glucose from getting filtered through. So what typically happens is we have glucose transporters in the beginning of our kidney tubules, in the proximal convoluted tubule, that literally grab glucose out of what is now ultrafiltrate and pull it back into the body. And under normal circumstances, if you have sufficient transporters and not a huge amount of glucose, you should be able to completely reabsorb it all before you end up peeing out any. Someone with diabetes could oversaturate those glucose transporters, and that could appear in the urine. You could also have someone who's eaten a bunch of sugar and then dumped it through their kidneys pretty quickly all at one time. That could cause an issue as well. So there are a few other reasons too, but those are the 2 big ones. In one case, the glucose, if you ate a whole bunch of sugar, it's normal to be there. In the other case, if you have glucose and you haven't, then you likely have diabetes, and that's not normal. What's interesting is that protein and blood, so if you're measuring it as hemoglobin, right, that shouldn't be in the urine either. But the reason why they're not there is they're not filtered in the first place. So normally protein or blood, it's just the formed elements of blood, is just physically too large to get through the filtration apparatus. It's sort of like, if you think about it at home, if you've ever made noodles, is taking the pot of noodles or spaghetti, and typically people dump it into what they call a colander or a sieve, right? And basically what happens is the fluid, because it's smaller, right, goes through the holes, and the noodles, the spaghetti, stays in the colander. And so that's what happens basically in our kidney for the protein in the blood. Sometimes you can get protein in the blood in your urine because that filtration apparatus is messed up, it's broken, and it's not selective anymore. And that's a huge problem from a physiological standpoint and a medical requiring thing. And typically, you're going to need dialysis or a kidney transplant in order to save your life. But it could be there as an example. Blood especially, if from menstrual cycle for women, or it could be there from infections for men or women. So associated with an infection would be white blood cells. And white blood cells, a bladder infection is very common in women. So the white blood cells would go into the bladder, because remember, they're capable of diapedesis. They can leave the bloodstream and go to the site of infection. So you've got this bladder infection where you have some sort of, bacterial infection inside your bladder. So the white blood cells go there, and one of the things they help to fight the infection are these proteins that they release. And so sometimes protein and blood go together, and it's not happening at the filtration apparatus, it's happening down the line in the bladder itself. And so again, in that case, yeah, you've got an infection, but that can be treated with antibiotics, or sometimes even not treated at all, and treated at home or something where it's not considered hugely dangerous typically for most people. So it could be there for those things. You can sometimes see in the urine, or very small amounts, and again, depends on how sensitive your strips are, bilirubin. Bilirubin is in your urine, sort of, but it's converted to a pigment called bilirubinuria. And basically, it's what makes your pee yellow. In addition, typically there might be some ketones in your urine as well, and that could be there for various reasons. So as an example, a diabetic would have ketones in their urine because they can't use glucose for energy, and ketones are typical of people that are using other fuel sources besides glucose in order for metabolism. So as an example, if someone was on a ketogenic diet, right? So you're having a low carb diet, or not eating a lot of carbs, or starvation diet, then you're going to be using other fuel sources, and you're going to have ketones in your urine, and that might be your objective. As a matter of fact, they sell literally, those chem strips for just ketones on the internet, so that people that are on diets where they're trying to actually get into ketosis, they can kind of test that with these little urine strips. And basically, it's just like we would do in lab. You pee on the stick, you look at the color and compare what it says. So it's pretty simple for that. So we don't expect to see much or if any of these things in bilirubin in urine. The bilirubin, it could be there as an example. Getting into the heading of too much information, but I have a genetic disease. It's a disorder called Gilbert's syndrome. And basically, when I fast, I don't make an enzyme that breaks down bilirubin. So I can have very high levels of bilirubin in my body, relatively speaking, yet still my body functions normally. And especially for like a blood test where, they ask you to fast for, 12 to 15 hours. And then, you do a urine sample, and, they always say I got too much, bilirubin. And you can tell the difference between someone who's got Gilbert's syndrome and other forms by looking at the conjugated and unconjugated bilirubin. We're not going to get into it here. I don't even worry about it, but just know there shouldn't be much of any of these things in the urine. And if there is, it could be something that's not very serious at all, or it could be something that's really, really serious and even life-threatening. Now, one of the things I also want to talk about is 9.2 of Fox, and we're going to hit this similar idea in lecture as well. But I want to talk a little bit about what we call clearance, okay? And in 9.2 of Fox, that would be the BUN or blood urea nitrogen clearance, all right? So when we look at the kidney itself and how much blood goes to the kidney, let's do a quick little math. So remember, the cardiac output of a human at rest is about 5 to 5.5 liters. And of that 5 to 5.5 liters, about a liter a minute goes to your kidneys. And so when we look at your renal plasma flow, right, it's about 600 mils per minute to the kidney, because 1 liter a minute is 1,000 mLs, right? And since plasma is about 60% of your blood, give or take, then the average person has about 600 mils per minute of plasma that goes to the kidneys. Now, we mentioned earlier that of that plasma, about 20% or so is filtered. It means 20% becomes ultrafiltrate, right? So looking at that number, right, 1/5 or so of 600, it's about 125 mils per minute. So this 125 mils per minute is a very important number. It's something you should get in your head, okay? This is called the glomerular filtration rate. We'll look at this value and what determines it a bunch of ways in lecture. Glomerular filtration rate is a homeostatically regulated variable. So we'll talk about how we do that in lecture again, whether we do it intrinsically or extrinsically, and what are the different ways we can do that. But one of the things to remember, it's about 125 mils per minute. This means we're filtering about 125 mils per minute into the kidneys, right? The average person, like we said, the urine production rate is like 0.5 ml to 1 ml. So what happens at other 120 to 124.5 mLs per minute? That fluid gets reabsorbed. Okay, so only a small amount actually gets excreted. But this number is important to know because we're always going to compare to figure out what's happening with the clearance value to 125 mils per minute. So that's the number you should get in your head, and we'll talk about enough where I'm sure it will be eventually. So again, we mentioned this before, the combination of filtration, reabsorption, and secretion determines the concentration of the various ions in plasma and urine, and ultimately determines your blood volume, which ultimately then determines your blood pressure. So those things are sort of related as well. So when we talk about clearance, clearance is this thing that doesn't make sense to students a lot of times. And I think sometimes, and I don't want to say this too often as a professor, but sometimes it's just best to just learn it and accept it and move on with your life. Clearance has this weird definition. It's the volume of plasma cleared of a given solute in a given time. So there's not a whole lot of ways that we can accomplish clearance, and physiologically there's even less. As an example, you can clear plasma from a solute by centrifuging, right? So we do that and we separate the hematocrit and then the buffy coat and then the plasma, right? So we can do that. We can't centrifuge in our body, right? We have no natural centrifugation properties in our body. So we do clearance by filtration, and that's how we end up with that. But what also then determines clearance is what do we get rid of and what do we through secretion and what do we reabsorb. And so those things, different things have to be taken into account as well. And so clearance has this very unique and very important equation. So clearance, that's the CL, equals UV over P. I was thinking that just a little stupid rhyme, UV over P, and that gives me my clearance. So U is the urine concentration in milligrams per ml. And to be honest, it doesn't matter what your urine concentration is, as long as it's the same as the P, the plasma concentration in terms of units. The U and the P are going to cancel each other out. So doesn't matter what you have. You can have it in moles per liter. You can have it in millimoles. You can have milliequivalents. There's just so many different ways you can measure it. But the idea is these are going to cancel out if they're in the same units, and they should be. So the urine production rate we measured from the laboratory already, so we know that. We also talked about measuring the absorbance of the standard. We knew the concentration of the standard because we got it from the manufacturer. And then the absorbance of the urine and plasma values, and then figuring out their concentrations for the purposes of using in this equation, basically. So again, let's look at the clearance of some basic substances. Okay, and here we're going to look at the clearance of glucose. All right, so if we look at some typical values, and we'll look at these, so a typical value for the urine appearance of glucose is 0, right? Because for 9.3, we said, well, urine should not have any glucose in it. So we would expect 0 milligrams per deciliter for the urine concentration. Urine production rate, right? A half a mil to 5 mils is normal. So 1 mil per minute, right? That's fine. It's a nice, easy way to calculate. And then plasma concentration of glucose, we said 70 to 100 is normal earlier this semester in lab. So we'll use 70 for that. So if we punch these into the calculator, right, we get U at 0 times V at 1. So that's 0 over P, which is 70, but it doesn't matter because 0 over anything is going to be 0, right? So the clearance of glucose is 0. So the volume of plasma cleared of a given solute, right, in a given amount of time is 0 for glucose because we haven't done that, right? So here's that calculation. 0 times 1 over 70 gives me 0. And so using the value of clearance, now we can assess what happens to glucose, okay? And the way you do that is you compare it to GFR. We said that GFR, we're always going to use the standard 125 mils per minute, okay? Again, mentioned before, memorize it. It's an important number that's going to help us for these type of things. So at 125 mils per minute, we're going to compare glucose to it. And if it's less than GFR, it tells us it was reabsorbed. So we compare our clearance value to the normal GFR, 125 mils per minute. Since it's less, we can say glucose was reabsorbed. Since it's 0, we can say it's 100% reabsorbed. So the farther away from the value of clearance for GFR, that normal value, the greater amount of reabsorption of secretion we have. So since it's less than GFR, it tells us it's been reabsorbed. Now we can also do it with other things. So here's an example of penicillin. Now, penicillin, I think most of you probably heard at one time or another that it's an antibiotic. We really don't use it anymore. We have better ones, but antibiotics, typically one of the problems with them, and one of the problems with penicillin particularly, is our body sees penicillin as a foreign substance and actually actively secretes it to get rid of it as fast as it can. So as you start to take penicillin, your body's starting to get rid of it just as fast sometimes. So let's say that the urine concentration we measured of penicillin was 600. The urine production, I'll just keep it 1, and the plasma concentration was 4. So we put that into the equation, right? Clearance equals U, V over P. So 600 times 1, U times V is 600, divided by 4, that's my P. That gives me 150 mils per minute. Since clearance in this case, 150, is greater than 125, it tells us that penicillin is secreted. So let's get to our data. So again, this is a quick review of it. So for the BUN, the blood urea nitrogen, We had a standard concentration of 50 milligrams per deciliter. We had an absorption of that standard at 0.04. When we measured the absorbance of BUN in the urine, it was 0.66. Putting that into Beer's law, using the standard absorbance and standard concentration, it comes out to 825 milligrams per deciliter. Since we've done Beer's law before, I'm not going to make you worry and calculate Beer's law in a lab exam. Okay, just know that's how we did it though, but I'm not going to make you calculate it. So we know that the urine concentration is 825 milligrams per deciliter. Since we're on urine concentration, we can go skip to plasma concentration because it's the same calculation. The only difference is instead of using the absorbance we got for the urine, 0.66, we use the absorbance we got for the plasma, 0.01, but the calculation's the same. So we get our plasma concentration at 12.5. Again, to figure out the V, that's my urine production rate, I just take the amount of urine, 36 mLs, divide by how long it took, 30 minutes, and I get 1.2 mils per minute. Okay, so if you punch in 36 divided by 30, you get 1.2 mils per minute. So then I can just replace these. The U, right? So I find the U is 825. The V is 1.2 mils per minute. The P is 12.5. So 825 times 1.2 divided by 12.5 equals 79.2 mils per minute. Again, in terms of the units, the U and P are going to be the same units. So both in milligrams per deciliter, here 825, here 12.5. They cancel out. You're left with the units here of 1.2 mils per minute. That's my V. So interestingly, blood urea nitrogen, which sounds kind of nasty, right? If you think about it, just sounds like something I want to keep in my body, right? Since its clearance, 79.2, is less than 125, blood urea nitrogen is partially reabsorbed. So it's reabsorbed. And our body is actually holding on to some of it. So again, pretty easy. All you have to do is calculate what the clearance is and then compare it to normal GFR. And if it's less, it's reabsorbed. And if it's greater, it's been secreted. Now, there's a couple other things to kind of talk about. And we're not going to worry too much about some of these other situations. So as an example, what would the clearance of protein be? And so what would it be? I'll give you a second to think about it. Okay. So how would I know that? Well, we've done some of this stuff before, got some normal values, so it wouldn't be too difficult to figure out. Okay. So how much protein should be in the urine? Well, we said earlier today that there should be none, so that's going to be 0. How much protein will be in the plasma? Well, normal is what, 6 to 8.4 grams per deciliter. So we can use some normal value there, which will make a difference anyway in a second. Urine production, right? You can pick any normal value between 0.5 and 5.0. And you'll get 0 times we don't care divided by we don't care. So you're going to end up with 0 for the clearance of protein. But in this case, it's different than glucose because protein is 0 because it was never filtered in the first place. We do not have the tools and experience in this class to decide whether something is going to be filtered or not. So the purposes of this class, both in lab and lecture, we're going to say, hey, everything's filtered for our purposes in terms of calculations. We're going to assume it's been filtered. All right. On the exam, if I ask you, hey, protein has a clearance of 0, why? You should be able to tell me it's never been filtered. But you don't have to consider that for part of the calculations. Okay. So that means that, we could have something that had a clearance that was equal to GFR. So what would happen if our clearance was equal to GFR? So again, let's kind of quickly review what we just talked about because this kind of shows it. So the clearance is less than GFR, right? GFR is 125. If it's 124 or below, that tells us we had net reabsorption of that substance. If clearance is greater than GFR, greater than 125, so that would be 126 and above, it tells us we have net secretion. But what happens in the case where clearance equals GFR? It equals 125 mils per minute. So you have no net secretion or reabsorption. Okay? If we assume that the substance was filtered, and we're always going to assume that, right? Then we can look at this. All right. So if my clearance value is equal to GFR, the substance is not reabsorbed and not secreted. And what's interesting about a substance that's filtered and not reabsorbed and not secreted, we can use its clearance value to calculate GFR clinically. The problem is there's no natural substance in the human body that does that. Sometimes we get kind of close with a substance called creatinine, not creatine, but creatinine. But we don't have any natural substance. So a while ago, scientists invented a substance that we could inject into people to do that, and it's called inulin. Right? It looks like insulin without the S. It's not a misspelling of insulin. It's called inulin. Okay? And it was developed to be freely filtered through the kidney, not secreted, not reabsorbed, because there's no receptors for it, because it's not a natural substance, and we didn't mimic a natural substance. So we can measure the clearance of inulin to measure GFR, and that's the nice thing about it. In order to be able to do that, right, the clearance should equal GFR. Right? So in a clinical situation, if you wanted to invent a substance where you could measure GFR, right? If you wanted to get in on the inulin business, right? And you gave it to 100 people and then measured its clearance in 100 people, you would expect, if it actually worked, right, to equal 125 mils per minute on average. If it didn't, then it would tell you your substance that you invented does not work. Okay? So if it's filtered, not secreted, not reabsorbed, the clearance would be equal to GFR, would be equal to 125 mils per minute, and then we could use the clearance of that substance to actually measure GFR clinically. Right? If it's less than GFR, we have net reabsorption, and if it's greater than GFR, we have net secretion. So here's some examples of different substances and what happens to them. So as an example, glucose has a clearance typically of 0, and it's filtered and completely reabsorbed. Urea has a clearance of around 65. I forget the exact number, but I think it's like 60-something to 80-something is normal urea clearance. So that tells us since it's less than 125, it's filtered, because it appears in the urine. We're going to assume everything's filtered and partially reabsorbed. For inulin, right, that's that synthetic substance that was invented to measure GFR. So its clearance should equal 125 mils per minute. And that tells us it was filtered, not reabsorbed, not secreted. I mentioned creatinine before, and this is the reason why we can't really use it to measure GFR, is because it's got a clearance value in humans of 140. In dogs, it isn't. It's very similar to GFR, but in humans, it's high. It's a little high. So an average number is about 140, which tells us it was filtered, and because it's above 125, over here it's partially secreted. And then for PAH, that's, don't have to know what it means, it's para-aminohippocratic acid, but PAH, don't worry about it, is a thing they typically use as a demonstration of something that's completely secreted. And its clearance is typically 600, and that means it's filtered and completely secreted. So those are some of the things that we worry about for filtration, secretion, reabsorption, and how we can measure GFR using those things. So we'll have some other clearance discussion in lecture, but that's Lab 27, 9.1, 9.2, 9.3, and FOX for that.